In this section we're going to look at separable equations, and these will allow us to derive some of the formulas we used for exponential growth, etc. These are differential equations of the form dy dx equals f of y times g of x, some function in y times some function g of x. And you can see why they're called separable equations, because you can actually separate the variables. And if we bring all of the y's to one side and all of the x's to the other, we find that the integral of 1 over f of y dy is the integral of g of x dx. And you can see that this is true for every function y satisfying the equation by differentiating both sides of the equation with the integrals. Well, when we perform the integration above, we get an equation relating x and y, which defines y implicitly as a function of x. And sometimes we can solve for y explicitly in terms of x, and sometimes we cannot. Let's have a look at an example. Suppose we want to solve the following differential equation. dy dx is the square root of x over 3y. Well, let's separate the variables. We multiply across by the 3y and we get 3y dy is equal to the square root of x dx, and integrating both sides we get the integral of 3y dy is the integral of the square root of x dx. And these are pretty easy to integrate. We have 3y squared over 2 equals x to the 3 over 2 over 3 over 2 plus a constant. Now, including a constant of integration is crucial here when solving these problems. Remember, the solution to our differential equation is going to be a family of curves unless we're looking at an initial value problem. Solving for y in terms of x, we have y squared is 4 over 9 times x to the 3 over 2 plus a constant. Then taking the square root of both sides, we get y is plus or minus the square root of 4 over 9 times x to the 3 over 2 plus a constant.